Alright, so today's going to be a video about nomenclature. So I'm going to be talking about the different types of compounds you have, or different types of functional groups. I say functional groups that you have. The main functional groups you need to know, for example, alcohols, aldehydes, and ketones. I'm going to talk a little bit about mechanisms. I'm going to talk about the type of isomers as well, and I'm going to talk about the properties of isomers as well. Alright, so first off, functional groups add a particular suffix to the end of the name of a compound. The functional group of a compound is the same. The functional group of the compound equals the part of the compound that reacts. So we give, for example, alcohol's name alcohol because the OH group, the functional group here, this is the functional group because this is the part of the compound that reacts. R just represents your side compound, or your main body. So if you have like a methyl group, or if you have a propyl group, that's just R, whatever it is. Aldehydes are a carbonyl group and a hydrogen bound to your R group. This is usually at the end, so it's never given like a 1. You don't have to write like 1. Whatever the compound's name is, just write end it with an L. So alcohol is OL, so ethanol, propanol. Aldehydes is always with an AL, so ethanol. Can you know ethanol? Yeah, ethanol, propanol, etc. Ketones are a carbonyl group between two R groups. So this here has a C. This one has a own, so it'll be propanone, so on. You can't have obviously ethanol, that doesn't work. But yeah, you don't have to write 1 or 2 for propanone because the same on either side. Because of this, certain ones only react in a certain way. So if you try to oxidize a ketone, nothing will happen because you can't break the carbon-carbon groups. With the reaction specific for the functional group, for example, like an aldehyde, if you try to oxidize an aldehyde, you'll get a carboxylic acid because you can break some of the bonds. And same with an alcohol, or not tertiary alcohols, but primary and secondary alcohols, you can oxidize them as well. You can reduce ketones back to secondary alcohols and reduce aldehydes into primary alcohols, but the functional group is the part of the reaction that reacts, and nothing else, really. Well, nothing. You just need to understand that here, the carbonyl group would have reaction, may form a nucleophilic addition substitution reaction where it breaks off its OH group, but you don't need to know about that right now. So the functional group of the compound equals the part that reacts. So therefore, different functional groups equal different reactions. For example, alcohols. Also have mechanisms. A reaction mechanism shows the formation of a new bond in a sequence that they're created. So, for example, here, if this is a nucleophilic addition mechanism, so it shows that the nucleophile has been added to the carbon. So it always goes from the lone pair to the carbon to show that the nucleophile has been added. You always write it from double dot, and also you have curly arrows. The curly arrows show that there's a movement of a lone pair, or movement of a pair of electrons. So going from the lone pair to the carbon, it's better to always make sure that it's a curly arrow, never a straight arrow, because even though the position is the same, it may get confused with the overall reaction, which this is just one part of the reaction here, just showing that the bond is forming. Alright. They also have different types of mechanisms. This is a bond breaking mechanism. Here you have 2 methyl, 2 bromo, propane. There we go. The Br is breaking off to then form this tertiary carbocation here, and you also get your Br minus group here. So this curly arrow really is what they're looking for, to show that the bond's been broken, so the electrons are moving to go into the Br minus and form this lone pair, or this nucleophile, to reform the nucleophile. So you can have bond forming, bond breaking, but yeah. curly arrow can also be used to show the breaking of a bond, as the free radical reaction. That other reaction was a free radical. A free radical is a molecule with with an unpaired electron. So you can have a heterolytic divide, but you don't need to know about all of that. You just need to know that it's just a molecule with an unpaired electron. That makes it very reactive. So that's one of the properties of it. It's a very reactive molecule. And an unpaired electron usually shows with a dot. So it's very important that when you're showing it's a free radical, you put that dot there. If you don't put that dot there, then you won't get the mark. It can be on either side, really. No one really cares, but you have to show that there's a dot there to show that it's a free radical. Yeah. All right, structure isomers. There's two types of isomers. There's structure isomers and stereoisomers. Structure isomers are molecules that have the same molecular formula but have a different bonding arrangement of atoms in space. There's three major structure isomers that you need to know. One is functional group isomers. Functional group isomers is when you have the isomers had their structures changed, so they have different functional groups. So, for example, here the same molecular formula for propanoic acid and methylphenolate, C3H6O2 and C3H6O2, but we can clearly see that there are two different types of compounds. One's a carboxylic acid and one's an ester. So you can see they have both the same number of compounds, the same number of atoms, but the one is a carboxylic acid group, COOH here. I'm not going to go over it fully, but that's the functional group there. And then you've got your ester bond here. I guess this technique part of it as well. This would be your R as well, but as you can see, different compounds there. These isomers had their structures changed, or actually I already said that. Chain isomers, molecules that have the same molecular formula, but one is linear and one is branched. For example, butane is a linear molecule with a molecular formula C4H10. Methylpropane is a branched molecule with molecular formula C4H10. So both here, butane and methylpropane. This is an example of chain isomerism because the same type of molecule, then there's not a difference in functional group, same functional group here, but one is linear, one is straight, and another one is branched. So that's just another type of isomerism. They do ask this like 1 mark questions in the exam. So be wary of these type of questions or these type of examples because it might come up in your exam. Position isomers, these are molecules that have the same molecular formula, but their functional groups are in different positions. So it literally is giving you the name. The functional groups are exactly the same. There's not really that much different in structure apart from the fact that the functional group is in a different position. So you can have butan 1-ol, which has the hydroxyl group attached to the carbon 1, like so here, and butan 2-ol, which has a hydroxyl group attached to the carbon 2. So these are technically two different compounds, and they do give different properties, as I'll explain later on. But yeah, so I mean physical properties, as in physical properties, not chemical properties. But yeah, butan 1-ol has hydroxyl group at carbon 1 and hydroxyl 2 group at carbon 2. So that's what position isomerism is. Stereoisomers. So this is a different type of isomerism. Stereoisomers are molecules that have the same molecular formula, same functional group, and the same functional group. That's a really bad example, sorry. No, I remember what I said now, sorry. So, stereoisomers are molecules that have the same molecular formula, same functional group, and same functional group position, but different arrangement of atoms in space. So they're pretty much the exact same, apart from the fact that you can't orient themselves in 3D space. this is a bit hard to grasp your understanding on, because you're looking at these two compounds here. If you're looking at, for example, for these two compounds here, you're probably thinking like they're the exact same, but they're not. Like you can't orient this. This is you can't move around the double bond. The double bond is fixed. So you can't move them around. You can't move them so they'll be the exact same thing. This is kind of idea is known as non-superimposable. So you can't reflect it. Kind of like your hands, you know. Your hands are always like a mirror image of one another. You can't do this and it'll be looking the exact same on the other side. You know, it'll always be a mirror image of it. It will never be the same. So that's what kind of stereoisomerism is all about. So yeah, alkene stereoisomerism. Did a little deals there, but so it can be viewed in alkenes. So you can see alkenes showing stereoisomerism. This is possible due to the presence of a double bond. Unlike single bonds, double bonds are rigid and can't be rotated around. So alkenes, CN, H2N, can display stereoisomerism at the double bond. For example, the simplest way to understand what this means is when you have an example. So below are the two different alkenes, E-butene and Z-butene. So the molecules are the same in every way apart from the position of the atoms. So a position of the atoms in space. So this is Z-butene and this is E-butene. So you think like, what does the E and the Z actually mean? E and Z just come from, you don't actually need to know this. You don't need to know it for example, but this is just, you know, you to actually just understand what it means. Might help you out. And this is how I remembered it in my exam for which way it was. E and Z come from the German words Entgegen and Zusammen. So yeah, for opposite, and so Entgegen means opposite and Zusammen means together. So an E alkene has the largest groups on the opposite side. So E, which means Entgegen, which means opposite side. So E just means opposite, Entgegen means opposite, so opposite side. Z means together, so Z means Zusammen, which means together. So and a Z alkene, as you expect, has the larger groups on the same side. No, so you shouldn't say side, or same side. And yeah, it's just German. The Germans invented this during the Holocaust. You don't need to know about that, but it's just something that if you invent, why is it German? It's just there anyway. Good way to remember this is that the Z alkene have large groups on the same side. If that helps out, but all you need to know, if you can remember that those only two words in German, zusammen, which means together, and entgegen, which means opposite, then it's a very good way of remembering it. But I don't know. So yeah, going back to this example here. This example is a skeletal formula, but I just want to show you what it is on the structural formula, on the displayed formula, not displayed formula, structural formula. So so E or Entgegen opposite. As you can see here, the heavier groups on either side. On this side, the heavy group is the methyl group. On this side, the heavy group is the methyl group on both sides. This is an E because, as you can see, the heavy groups are on opposite sides. They're not on the same side. They're on opposite sides of the double bond. So you call this an E isomer. This here would be Z isomer because the heavy groups are on the same side of the double bond. You can't, and before you say these are the same molecule, they're not, because you can't rotate the methyl group. Like, you can't, because the double bond can't be rotated. The methyl group, the double bond between the carbon here in butene can't be rotated. In the butene, I should say, can't be rotated. So because of that, this will always be on the same side, and these will always be different molecules no matter how many times you try to rotate them. Therefore, the methyl and hydrogen can't switch positions, and therefore these are two different molecules. So when you actually need to, one thing you need to know is something called the Kahn-Ingold pre-log rules, and they help assign the E and Z isomerisms to more complicated molecules. If you need to know which group is the heavier group, because sometimes it's not always going to be easy to say CH3 is the heavier group and H is the heavier group in here. You might get, you know, Cl minus, which is quite a heavier group than just a methyl group. So you need to know how to actually determine whether or not you have a certain group which is heavier than the other. You call that the Kahn-Ingold pre-log rules. The Kahn-Ingold pre-log rules help assign EZ isomerism to more complicated molecules. They help distinguish between E and Z isomerism for more complicated cases. Yeah, I'm gonna stop this video and then split it into two actually. So this is the end of part 1, I guess.